The heat is usually calculated using this formula of Q is equal to mc delta T, where m is, of course, the mass of the material, delta T is the change in temperature, and the C is what we call the specific heat. Now, specific heat is characteristic for material, and it is a physical property of that material that measures how much heat is required to raise the temperature of 1 gram of that material by 1 degree of Celsius. And therefore, normally the unit for C is joule over gram Kelvin, or let's write it this way. Joule, gram power to the minus first, and Kelvin power to the minus first. Now, another way to express heat is using the mole instead of the mass of the material. So Q is equal to N, in this case Cp delta T, where N now is mole, and you use this instead of the mass, and Cp is what we call the molar heat capacity. Molar heat capacity is how much heat is required to raise the temperature now of 1 mole. 1 mole of a substance by also 1 degree of Celsius. The unit for Cp is joule mole power to the minus first and Kelvin power to the minus first. Now, importantly, as you work through the exercises that we will discuss in our meetings, the heat capacity and also the molar heat capacity, they will have the same numerical value whether the temperature is expressed in Kelvin or degree of Celsius, because the heat depends on a difference of the temperature instead of the temperature itself. And whether you use Kelvin or degree of Celsius, the difference in temperature will give you the same numerical value. Now let's take a look at an example where we have, for instance, a glass of water with a warm water inside with the temperature of 78 degree of Celsius, and we have a piece of metal, for instance gold, which is cold with a temperature of 2 degree of Celsius. Now, if we put the gold into this water, at the end we can measure the final temperature by the system, for instance becoming 76.9 degree of Celsius. Now, in this case, the heat will flows from the warmer system, which is the water, and the heat will be received by the gold. Now, assuming that the heat only flows between the gold and the water with no heat lost or gained from the glass or the surroundings, we can write that the Q of the gold is the same with the minus of the Q of the water. So for each, we can calculate that the mass of the gold multiplied by the C of the gold multiplied by the delta T of the gold will be the same with minus mass of water multiplied by C of water multiplied by delta T of water. Now, the delta T for the gold will be the final minus initial. So, 76.9 minus 2, while the delta T for water will also be final minus initial, which is 76.9 minus 78. So again, delta is a symbol for subtraction between the final value minus the initial value. Now it's your turn to try to solve this problem. A 125-gram sample of cold water and a 283-gram of sample of hot water are mixed in an insulated thermos bottle and allowed to equilibrate. If the initial temperature of the cold water is 3 degrees Celsius and the initial temperature of hot water is 91 degrees Celsius, what will be the final temperature? So your task is to calculate the TF. The measurement of heat flow is called the calorimetry. The instrument is called the calorimeters. Here's the simplified diagram of what we call the bomb calorimeter, which operates at a constant pressure. So we have the system inside that is illustrated in the red color, and this will release the heat into the surroundings, which is inside the yellow square, and there is no heat flow to the outside of the calorimeter. In this case, minus of heat of the system will be equal to the positive Q of the surrounding. Because heat will be released by the system, and because there is no heat flow to the outside part, the released heat will be accepted by the surroundings. There are two steps in using calorimeter to measure the heat flow. The first one is the calibration step. The calibration allows us to determine what we call the C of calorimeter, or the constant of calorimeter, with the unit of joule over degree of Celsius. The calibration can be done either by burning a known amount of a well-characterized material or by resistive heating, in which a known amount of current is passed through a wire that heats due to its electrical resistance. From this, the heat capacity of the entire calorimeter may be obtained, which is symbolized as Ccal, where the Q is equal to the Ccal multiplied by delta T. Note that in contrast to our earlier equations, there is no mass or number of moles in this equation. The calorimeter constant is the heat capacity of a particular object rather than that of material, so it may help think of it as the heat capacity per calorimeter. In the case of bomb calorimeter, like we see in this diagram, the calorimeter constant is largely attributable to the water also that surrounds the bomb. It also includes the heat capacities of the thermometer, the steering system, and the bomb itself, so we do not have to multiply it with any mass or any mole. Now, once the calorimeter constant is known, we are ready to use the calorimeter for the second step, which is the actual measurement. In the actual measurement, we place a known amount of reactant, mass or mole, into the calorimeter, initiate the reaction, and then we can measure the resulting temperature change of the calorimeter. Now we know that the Q released by the reaction inside the calorimeter will be equal to the minus Q of the calorimeter. So we can find the heat being released by the reaction by calculating the heat received by the calorimeter which is equal to the C of the calorimeter multiplied by the change in temperature happening in the calorimeter. And from here, we also can calculate what we call the energy density, which is equal to the minus Q of the reaction divided by the mass of the material. To understand better about the concept of calorimeter and calorimetry, let's try to solve this problem. The combustion of 1.05 gram of naphthalene, C10H8, produces a temperature rise of 3.86 degrees of Celsius. This process releases 5,150.1 kilojoule per mole of heat. Now, burning a 1.83 gram of sample of coal in the same calorimeter causes a temperature change of 4.90 degrees of Celsius. The question is, what is the energy density of the coal? You can pause this video if you would like to try it on your own first. Okay? Notice that the first part here is actually the calibration part, and this part of burning the coal is the actual measurement part. So we know for the calibration, we can calculate the C of the calorimeter, which is equal to the Q divided by delta T, because Q of calorimeter is C cal multiplied by delta T. So we know that combustion of naphthalene actually releases 5150.1 kilojoule per mole. Now, we don't have 1 mole. Instead, we have 1.05 gram of sample, and we know that this causes the temperature rise of 3.86 degrees of Celsius. So first, your task is to convert this value to the mole of naphthalene. Take the mass of naphthalene divided by the molar mass of naphthalene, and then you obtain the mole of naphthalene. You know that for 1 mole, the combustion will release this amount of energy, kilojoule. So then you can calculate how much energy will be released for N mole that you calculate from the mass divided by the molar mass. And don't forget to convert this into joule by multiplying with 1000. Now that you have obtained the amount of energy, which is the heat, you can calculate the C of calorimeter, which is the amount of energy divided by the change in temperature, which is 3.86 degrees of Celsius. So this is the calibration part. Now into the coal burning part. We know that Q of the coal will be minus the Q of calorimeter. The Q of the coal will be minus C of calorimeter that you calculate from here. Now multiplied by the delta T caused by burning of the coal, which is 4.90 degrees of Celsius. And from here, you can obtain the heat evolved by the burning of the coal. And lastly, you can find the energy density of the coal by dividing the Q of the coal. Don't forget this has to be positive in value, divided by the mass of the coal. Or you can also write it down as minus Q of the coal divided by the mass of the coal, because the Q of the coal that you will obtain from this equation will be negative as the coal is releasing heat upon its combustion.